way of getting to a comfortable area in order of magnitude in risk was through improving gate reliability and improving emergency action planning. And that is the case many times. We are aware, but what brings risk to us, quantitative risk quantifies it and makes it very important. So EDELCA shift the focus problems since the late 60s. And all this, I'm sorry, I can point there. Is the way you diminish risk by doing things. So believe it or not, after 30 years, what was the ignition of an action plan, of spending money, of doing things, was that graph, in which you see the rate you can and how much you can diminish risk with your actions. So there's another magic in the numbers, which is, believe it or not, there are drivers of action, almost in anywhere. This study, for instance, is in the public domain. That's another lesson. Transparency, being auditable, not having fear to show the way you made your decisions. That's smart, nice, modern governance, and that uplifts or lifts dam safety to a higher level of governance. Other system with a lot of similarities with some of the projects maybe in other countries in which there's a lack of data, but you have a so critical project that if they would fail, they would flood 1/3 of the total surface of the country. And you might not have a fully probabilistic approach. You might not have the inter-basin characterization of the flow as you wish, but you cannot wait 20 years to decide if you wanted a new spillway or not, or if it makes sense, or where it's more efficient to start with the emergency action. So, accounting for uncertainties, assuming that we might be an order of magnitude right, or if you wish, an order of magnitude wrong, but we are not so much out of the picture. When we put this graph to the owner, we build the numbers with them, and they assume they are very far right in terms of affected population, and they are clearly, no matter the exact number, above where they wanted to be in terms of probability of failure. Again, you can account, you can demonstrate the impact of your investments. If you see the horizontal movement, that's only with emergency action plan. And it's not the same to say, I want to do emergency action planning because it has to be done. That's saying, in my particular system, I can reduce risk in 2 orders of magnitude. And that's a very compelling argument, 2 orders of magnitude. And then the other things that will take a little bit more time, they will be complemented with data. There's something with the gates that can already be done, something with the operating rules, and that's the path the cash, which is a very strong public company in Albania, are moving forward and motivating their human resources. So that's the path. And once you can plot the path, motivation of people increases. More things about the scale. For instance, this is Tegucigalpa, Honduras, and they wanted to have a risk perspective only from the urban, more consolidated area perspective. But they would be getting a very wrong picture if they don't understand that these 2 dams, formerly far, have been embedded by the city. So what you have is people living exactly in front of the spillway. You have a dam you cannot renounce because it is a water supply dam for the whole city, but you have embraced it with population, and the risk is 2, 3, 4 orders of magnitude higher of what you wanted. So what do? First thing is don't say risk analysis is guilty of bringing the topic. The topic was there, quantification helps, and from there you can enforce urban policies, early warning, with a rational approach behind. So they were brave enough to accept it and to have a more holistic approach to the urban flood risk, understanding the impact of what had happened from an urban point of view and the implications in policy and other non-structural measures. More things. This is Argentina. This is another different thing. This is we were working for the regulatory authority, and they had been discussing for a decade about a spillway upgrade because they had two major floods they were about to overtop, but nobody had quantified what was the real or the most real we can get to the hydrological risk. So see that's people working together. That's identification failure mode. That's teams from the regulatory authority, but also from the owner, also consultants and universities getting together to do the failure mode assessment and crunching numbers together. Another value I want to bring to the audience is that by the time, if you are doing a collaborative approach on risk, by the time you get the number, the estimates on where you are and where you want to be, you already got the consensus if you have done it together. And don't underestimate the value of consensus if you want to reach an agreement and if you've been working together. Because if there's ownership on the results of risk by the different parties, it will smooth the path to a negotiated solution. So that's exactly what's happening in this very iconic project in Patagonia today. So, coming to this, though this graph is very nice because it ends up with the word success, but denying the complexity and the problems would not be nice either. I wrote this paper with a colleague in the Corps of Engineers, Eric Halpin, who is in charge of the dam safety program for 400 dams, and the ontology, which is a definition, a proper definition of risk. The complexity, the uncertainty, the ambiguity, the tolerability issues, all that is not brought by risk analysis. It's there, but risk makes you address it either if you like it or not. Second thing, and most important, is the last quarter, is the people, communication, and decisions. This is a joke I always make. You can do 100 of articles and PowerPoints, pretend you are doing dam safety, you are not making any real decision, and nothing happens. So either you have decisions and real investments at the end of the pipeline, or you have nothing. Either you have people engaged and capabilities, or you have nothing. Either you communicate it well, or it doesn't work. And that is important. To me, the most important is to go through the first loop. People get stuck. I've seen people saying, it is too complex. Then they stay there forever. If you do your first loop, I'm sure you will do much better in your second loop. And the leading agencies are today because they went all the way through the first loop. And that's my personal experience also. Final remarks, doing it. If you don't go to the end and make decisions, you're basically doing PowerPoint dam safety. Bringing innovation with manuals, with guidelines, with legislation. Innovation is not only algorithms. Innovation is not only on the high cutting-edge technology. A good way to do things, a shift of paradigm, a conceptual approach is innovation. And this type of governance of dams is fueled by innovation and knowledge. And that's another collateral good you cannot forget. It's not a recipe, a cook recipe. It is how to incorporate knowledge in the chain constantly. And again, Let's go back to globalization. So many people talking badly about globalization lately, right? Let's not underestimate the incredible learning curve that it allows us to have. You don't have to copy paste. You can bring best practices all over the last half century. Do it your way, be creative, and be leader very fast and do things better than others very fast. So paradigms shift in practice, and whenever you are tempted to say, oh no, but we are doing better than 10 years ago, just ask to yourself, is that good enough to cope with your real challenges? So go for it. That's my final thing. Thank you very much. Now I will be controlling others' timing. So please welcome Dr. Hadous. What I would suggest, Dr. Hadous, if you want to use first minute to introduce yourself, so we do this more dynamic, that should be fine. And then I will count the 10 minutes afterwards.
Can you check? Oh, no. Okay. Yeah. Sorry for the inconvenience. Thank you so much. I'm very happy to be here. First of all, I would like to thank the panelists and for their invitation. And my name is Hadoush. I work for DRIP project in Aegis. So I'm working as it's okay? The construction management and quality assurance expert for Aegis. So because there is no much time, so I think this introduction is enough. So this shows the outline of my presentation. I don't want to waste time on this, but I want to give some introduction. So as you might have seen, the title of my presentation is Liquefaction and Permanent Deformation Analysis of an Earthfill Dam Subjected to a Strong Earthquake. So in the morning we have heard that pseudostatic analysis is obsolete. I think Dr. Martin was saying that. Well, I would not say, I'm not going to repeat that, but we need to do dynamic analysis, at least for dams designed on potentially liquefiable materials or complicated geologies, or where you have high seismic areas. Okay, now just to give you a small introduction about earthquake engineering in dams. So in the first dams constructed in the first 6 decades of the 20th century, that means up to the 1960s, they were found to be deficient in terms of earthquake design and flood design. Of course, about flood, many people have been promoting it, and we have done additional spillways. We have improved many dams to help them behave against extreme floods. But in terms of earthquake, maybe it doesn't happen like floods every time. A lot has to be done. Well, something happened to this slide. So the first time earthquake engineering was considered in dam design is in the 1920s. And that's when we have started in the 1930s the pseudostatic analysis. Now, in the 1960s and 70s, when Ignacio was saying that was his birthday, 1971, and I was born 1970, some earthquakes happened and some failures also happened in dams. Then people started to think that the pseudostatic analysis may not be sufficient, or it may not always predict the behavior of dams, and they tried to think other methods. About the same time, in the 1970s, while we were born, new technologies in terms of high-speed computers and finite element method were emerging, and this gave interest to do dynamic analysis. Some examples of earthquake are the Alaska earthquake, which is very large, 90.2 magnitude, and Niigata earthquake, and these earthquakes brought focus on liquefaction of soils. And the lower San Fernando dam failure, because of the San Fernando earthquake, also brought some attention to earthquake designs for dams. So the main objective of this analysis, or basically of dynamic analysis, is to do two things. Number one, to analyze whether there are potentially liquefiable soils in your dam or foundation. And number two, how much will the dam settle, or how much displacement will be occurring on the dam, so that you don't lose your freeboard. So let me show you this as an introduction again, the San Pablo Dam in the US. So what you see here is, it's, so initially, this is a dam that, if you see, so this is the initial dam. So in 1967, after the earthquakes happened, they added this buttress. So we wake up when we see something. So we learn the hard way. Maybe that's, okay, Ignacio was saying it's not that reason, but I think people wake up when they see disaster. So because of those earthquakes, they added this small buttress here. Then they stayed for many years. Again, after the San Fernando earthquake, they added another buttress here. They dug out all the foundation. This is alluvial foundation, which is potentially liquefiable, and this is hydraulic fill dam. So in 1979, they added another thing because of some failures. And finally, in 2010, they added other mitigation method on the downstream part. This is upstream is on this side, downstream is on this side. So they added cement soil mix, but it's a very deep soil, so 35 meter. So they had to solidify the dam foundation. So this is just giving you an example how we behave to the behavior of dams. We act when something happens. Now, that is the introduction. Now I will take you to my analysis. So I'm considering one dam in my country, Ethiopia. It's a zoned earthfill dam. It's about 53 meter high, and it stores about 1.8 billion meter cube, or 1,800 million meter cube, to irrigate 60,000 hectares of sugarcane. And this dam was designed by Ethiopian experts and Indian experts from WAPCOS. So WAPCOS was part of this design. This is a section of the dam. It's a zone dam with clay core inside, shelled by sandy gravel soils. And these are the different parameters of the dam zoning. And this is dam geology. It's very important. So this is a dam foundation geology. It has three important components. The first one is this part, which is alluvial foundation. The second part is this part, which is what we call lake sediment, sandstone, mudstone. And the third part is basalts below all these different types of basalts below these two layers. Our attention is on this top layer, which is alluvial deposit, the behavior against earthquake. Oh, okay. So to do dynamic analysis, I don't know why my PowerPoint is messed up. Sorry. So we need peak ground acceleration. So we had to determine the peak ground acceleration for this site. So the horizontal peak ground acceleration is 0.3 g for the site. And there are two earthquakes that we have to consider according to ICOL recommendation. The first one is maximum credible earthquake, which is the maximum expected earthquake in that area. And the second one is a design-based earthquake, which is earthquake that's expected to happen in the life period of the dam, which is 1 in 500 return period. So under these two earthquakes, the dam, under the design-based earthquakes, the dam should be stable, it should be operational, even if you tolerate some damages. And under the maximum credible earthquakes, the dam should not fail because of liquefaction, and it shouldn't lose its freeboard. Now, that's only the peak ground acceleration, but to do a fully dynamic analysis, you need acceleration time history spectrum. So you have to have the whole acceleration time history. Well, earlier it was said there is no data. We didn't have the full acceleration time history data, but we didn't give up. So we had to use some data from elsewhere. So we have used 3 earthquakes. The first one is 1940 El Centro earthquake. The second one is in Japan, Hachine earthquake, and the third one is again in Japan, Kobe earthquake. But you cannot just take the earthquake from El Centro and apply it in Ethiopia. You have to remove the site and geology effects in El Centro. So we have to do the so-called deconvolvation. So all these earthquake data are deconvolved. It means the geology and site effect was removed, and they were taken back to the bedrock, so you can use and apply it in other places. So this is the acceleration time history we have used for the analysis, and these are for the 3 earthquakes. Before we did the dynamic analysis, we did a very small analysis based on grain size. So these basic tests also help you. So what you see here is 4 boundaries. The internal 2 boundaries are showing for most liquefiable soil will be inside these 2 boundaries, and external ones are potentially liquefiable soils. So we have done analysis based on these curves for the dam and the foundation. So this is analysis based on this envelope for the dam body. So as you can see, the envelope is between here and here, but the dam shell materials are mostly outside of this envelope, so we didn't consider them as potentially liquefiable soil. But if you consider the dam foundation, it's 85% is within this boundary, so we had to consider it as potentially liquefiable soil. This was the finite element model we have used was for the analysis. And you have to have so many parameters, dynamic parameters. One of them is shear modulus, and we have used some empirical equations which are established based on a lot of research in other countries. So these are the parameters for the behavior of the soil. This represents shear modulus reduction versus damping ratio of a given soil. This is for the clay core, and this is for alluvial foundation and for the stone. Now the analysis results, where we have reached somehow on the results. So the first thing we have evaluated is what is at the bed was 0.3 G, what happens when it's at the dam crest. So as you might all know, there is always soil amplifies the earthquake. So it was 0.3 G at the beds, but when it comes to the dam crest, where you have spillway and other structures, the peak ground acceleration becomes close to 0.9 G. So there is a lot of amplification in this structure. So it is the same for both cases. The second result we found is the foundation alluvial completely liquefies. So this yellow color shows you how the alluvial foundation liquefied completely. So this dam was constructed in 2010. It was finished. So just before that, we did this analysis, and we had to remove the whole alluvial foundation before they completed the dam. So we gave them this advice, and it was helpful for the dam. And we have done some effective stress time history. You can do in this finite element, there are so many options you can do. So we were trying to study the effective stress time history for the liquefied zone. So as you can see, the acceleration time history hits the 0, where that's the effective stress is 0. That's when the soil behaves liquefied. So the strength of the soil depends on the effective stress. And we have done some liquefaction time stages, and until the 13th second for the maximum credible earthquake, there was no liquefaction. But once the effective stir hits zero level, then the soil was liquefied. The second component, which is important, was to determine the permanent displacement, how much you lose the freeboard. So we have analyzed several slip surfaces that start at the dam crest and end at the toe of the dam, and those that start at the dam crest and end at the berm of the dam. So the most critical slip surface was this one. It involves almost 50% of the dam crest, so your freeboard is much affected, and it settled about 70 centimeters. So this 70 centimeters should have been added as part of the freeboard. So this was not considered initially. We had to add 70 centimeters to raise the dam to account for this settlement. So as a conclusion and recommendation, am I okay? Oh, okay. So what we did is we removed the completely liquefied foundation soil. That's number one. But we were lucky to do that because it was not deep. You cannot do everywhere. You cannot remove from existing dams, for instance. So you have to do other remedial measures for that. And the vertical displacement, we have added it in the freeboard. There was parapet wall 1.5 meter. We removed it because if the slope fails, it won't help for the freeboard. So, and because there was big horizontal displacement, we had to add about 3 meter filter to account the cracking of clay core. Thank you so much.
Thank you for that, Justin. As we are taking a couple more minutes, each of us, I was thinking if there's a very, very fast question that somebody cannot wait to make, we can take one. Otherwise, we wait till the end. So let's wait to the end. Again, if there's one super fast question at some point that you really need to make, we'll take one per speaker. Next speaker, it's my pleasure to welcome my co-chair, Dr. Mukesh Kumar. I'm going to ask you to introduce yourself to make it more dynamic, if possible. Thank you very much.
Sorry, one second.
Well, very good afternoon. I won't take much time and it's straight commentary. In fact, the dam which you see in the podium is this photo of the Sardar Sarovar project. And I'm going to present what action we have taken to ensure the safe filling of Sardar Sarovar Dam. In fact, you all know that the first filling of a dam is very important because that is the first indication how safe the dam has been built and constructed. And Sardar Sarovar has the checkered history, so we have to be extra careful in the first filling of the dam. A brief introduction about the Narmada Basin. It has got 30 large dams, 135 medium projects, and over 3,000 minor schemes. We have got many important dams, and Narmada, the Sardar Sarovar Dam is the terminal dam. Most of the dam upstream has already been constructed, so this particular dam had more importance attached to it. In fact, the dam has very close to the hearts of our Prime Minister, and recently he has dedicated to the nation also. It is an interstate multi-purpose project. It has got the 4 party states are involved in it: Gujarat, Madhya Pradesh, Maharashtra and Rajasthan. You can see from the benefits which is there, 18.45 lakh hectare in Gujarat, 2.46 lakh hectare in Rajasthan. Power also 1450 megawatt, and drinking water to 131 urban center and 9,633 villages in Gujarat, and in Rajasthan also 2 urban center and 1,107 villages drinking water is there. There has been a dispute, and we have the Narmada Water Dispute Tribunal, which gives about the salient features of the project: allocation of water and power for SSP, regulation of Sardar Sarovar Dam, and apportionment of the cost also. And as I have said, that it has got very checkered history of construction. It started way back in 1961 with the laying of the foundation stone by the then Prime Minister Pandit Jawaharlal Nehru. It has made a very slow progress, and finally it reached to some level in 1995, that is the 80-meter height. But at that time also it got stopped because of the Supreme Court intervention. There were issues regarding environment and rehabilitation, and the project got stopped. It got the clearance only in 2000. So every 5 meters the construction was done, and the concept of pari passu completion, like as you complete the environment and safeguard measures and complete the R&R, the dam raising was allowed, started in that. Finally, thereafter, the authority to permit further raising of Sardar Sarovar Dam was given to NCA, and the subsequent permission was given in 2002, and about raising to 100 meter in June 2003 also. The photographs below are there at different stages, the construction which has proceeded ahead. 2004, the permission to raise up to 110.64, that is minimum drawdown level, was given. But the actual benefit started in December 2006 when the dam level rose to 121.92. And finally in July 2016, the permission for installation of gates was given. The photograph which you see down below on the left side as well as in the podium below was given without the bridges. The gates are constructed. Now the gates have been there, and the dam has been inaugurated, dedicated to the nation by the Prime Minister. When the permission for final raising was given, the Narmada Control Authority, which was given the power to give the permission, made a very specific recommendation with regard to safe filling. It gave the responsibility to Sardar Sarovar Reservoir Regulation Committee to ensure that the phase filling of Sardar Sarovar Reservoir added with it the dam safety inspection and the proper monitoring of actual submergence is there. So safe filling was duly recognized while giving permission, and the responsibility was given to Sardar Sarovar Reservoir Regulation Committee of Narmada Control Authority. Naturally, we looked into our Indian standards and international best practices. We have our Indian Standard Code which prescribes. It also has, we have Central Water Commission guidelines also. Those guidelines are primarily for earth and rockfill dams, but has been extended because this dam has the checkered history. The construction got stopped at several places, and so we have to be extra careful in letting the dam fill in the first time itself. So we planned a kind of a phased filling also. So we took the following criteria. Since 121.92 was already there since 2006, 10 years has passed. So we said up to 121, we can go straight way. Thereafter, in one flood, we has reached 131.18 meter. So we said that next stage, we can be at 131 meter. And then hold on period for about 10 days at that stage when the dam safety inspection could be carried out and the submergence monitoring could be also be taken out. And thereafter, further filling with only 30 centimeter in 48 hours. That kind of filling was planned. If you see the graph also, the planning was done, the minimum drawdown, the spillway level was already reached in 2006. So first there, hold on period, and then finally the gradual filling of the dam was planned in this thing. The dam safety inspection was also carried out during the hold on period. It was inspected by the dam safety panel. The operation of gate was tested by slight opening. Inspection of dam galleries was there. Seepage was found little more. The most important recommendation was the revival of instrumentation. In fact, most of the instruments do not function, and the panel did recommended how we can revive it and how we can introduce the instrumentation at this stage. I think probably the lesson is for us that when the dam is being constructed, we should be extra careful, rather more than careful about having the instrumentation also. As a substitute, we had the geodetic monitoring, but geodetic monitoring only gives the surface deformation. Of course, that was very well within the limits, and it also proposed sedimentation survey of the reservoir and preparation of O&M manual of Sardar Sarovar Dam. So these are the first dam safety inspection after when the permission of the filling of the dam was given. The monitoring of submergence through remote sensing was also attempted. This is for the first time that submergence filling is being monitored through the remote sensing. So we requested the BISAC to take the satellite pictures monitoring monitor the filling part of it, and see how the rehabilitation and environment safeguard measures has taken pari passus there. So if suppose any island is forming or any landslide is happening anywhere, we will come to know immediately, and then corrective action on the periphery of the reservoir could also be there. This was also, submergence model was prepared on a real time and was monitored, and in addition the state governments prepared the contingency plan also. Thank you.
Thank you for being so respectful with the time also. Any very, very quick question, or we kept all them till the end? Okay. One very quick. Can you help him?
Slide change.
Please introduce yourself also.
I have to flag 3 issues in this. See, you mentioned about raising the dam in different levels. That lift joints, this is the first dam I ever find, the seepage is so high, a non-overflow section, a sheet of water is flowing and they are observing with a V-notch. Now how this issue is going to be addressed, because it's quite serious. Lift joints, all the joints are leaking very badly. That is one. I'll give you all the 3, you can respond, please. What is the action plan for that? And number 2 is, this dam is not integrated with the DSO of the state, and there is a lot of reluctance to it. Dam safety, you know, this dam having been completed, it should be integrated with the dam safety organization of the state. But there is so much reluctance there. Okay, that is number 2. Then number 3 is, how reliable is this geodetic monitoring? Because there is no plumb bob, there is no way of measuring deformation, right? They are depending on the indirect method of geodetic surveying. How far this can be relied upon? Thank you.
Sir, I think you are very right, and as if you recall, what I have presented is also, the dam safety inspection was very important, and we did it. And regarding your first is the heavy seepage which is occurring. We have taken note of the observation, and as I have said, because the construction has been taken in the stages, so there are problems, and naturally we have to address the issues of heavy seepage also. We have taken note of it, and we are in touch with the state government, particularly the project SSNNL, which is managing to take effective corrective measures on that part. The second part which you have said about that, geodetic monitoring, I really fully agree with you. In fact, we should not rush up the construction just because and rather spoil the instrumentation system. This point, as a director CWPRS, I raised in the Polavaram also, that we should have adequate number of instrumentation and take care. Unfortunately, there also probably the concept was for speedy execution. That's why I flagged it also, that during the construction phase, we must be very careful about the instrumentation and their safe operation. The third part, of course, is merging with the state dam safety. That is still under consideration. Sardar Sarovar enjoys a special position. Certainly it will have a special panel, and we are working with the state government to ensure that a special monitoring is being done for the Sardar Sarovar project. I hope we can further discuss on this thing. It is just the first time it has been feeling started. It has got its own history of conflicts and problems, but I hope with the working with the state governments, we can sort out all the issues and may ensure the safe operation of the dam.
Okay, thank you. We keep going. I said, and for the next ones, please try to make one question. No, that's for the end. I mean, okay. The other thing you can do, please, that I forgot, please write your questions in the notebook that you have, and we will gather all them till the end. Please do it. Please do it. So let's welcome our next speaker, Dr. Sharma. Please introduce yourself and Make a good use of your 10 minutes.
So, very good afternoon. I am ML Sharma. I'm professor of Earthquake Engineering Department in IIT Roorkee. I joined that department in '85, and since then I am teaching engineering seismology, earthquake engineering to the students, and also practicing earthquake engineering. I had been consultant to more than 300 dams on seismic hazard issues. This talk is about the seismicity studies for projects. So as you know, the seismicity means the earthquake occurrence. Basically, you want to know what type of earthquakes are occurring around your site, because while calculating the seismic hazard, you are using the seismicity information and giving the seismic hazard values to the earthquake resistant design for the engineering project. So it is very important from that point of view. Just to have the same frequency of our talk and to go back in the time range and the time scale, the earthquakes are happening, and if you see on global level, the seismic hazard values in India, they are quite high. You can see the red portions here, that too in the Himalayan range. This gives you the idea about how much earthquakes they are happening. And the reason being is the Indian plate going towards the Eurasian plate. So it was around 70 million years ago that it started and collided with the Eurasian plate around 10 million ago. And then the start of Himalayas started, and the earthquakes, they are occurring since then. There is no place in India now where you can say that there will be no earthquakes. And it is quite clear from seismic zoning map of India also, and more than 70% of the area comes under the high seismic zones. And you can see the earthquakes, more than 7.5, which have happened in India. And they are because of the motion. And these motions, they have been worked out using GPS, using old techniques, triangulation techniques, which civil engineers, they use. And it's all because of the plate motion. So with this background, let us see what we do in seismicity studies. We are monitoring the seismicity in the environment of the engineering project. We want to delineate the seismic sources, because these we will be using to calculate the earthquake forces for design purpose. Then studying these sources for their physical process, how they are happening, what type of physical process is going on, including the sense of motion near to the dam. Then studying the medium characteristics, how the energy is attenuating in the medium, how the energy is amplifying in the medium. And then some of the portions, if you go for longer time for the monitoring of seismicity, you can tell about whether there is a reservoir induced or triggered seismicity or any other phenomena. So hazard is the basic thing, and because it is a dam safety conference, so if we want to estimate the risk, then hazard is one of the important factors. So what we need is to mitigate the seismic disaster. And because there are a lot of development in earthquake engineering, and we can make use of the ground motion and best use of it for the seismic resistant designs. We have very nice modern equipment nowadays with quite a good dynamic range, with a very good resolution. And then we are having mega investments in these engineering projects. So for the seismic safety, Seismicity studies, they are one of the very important part. Now what we get out of it? The deliverables, we get the design parameters first based on the past seismicity, and then we go on looking into the dynamic system and go on changing. That's the question what I asked in the morning session also, how frequent we should go for seismic hazard reevaluations. Then we should know the contemporary seismicity around it, then their temporal and spatial behavior, then the geometry of the sources just below the dam, so that we can do some disaster mitigation, and the medium characteristics. So in this regard, I will be taking the Tiri as the example. You know, Tiri is in Himalayas, and a lot of problems were there while it was coming up because of the Himalayan tectonics, because of the highest magnitude which should be taken for this, because of the distance, the lowest distance which should be taken for estimation of the ground motion. And for all this, we must have these seismicity studies, because we have used the data in the past, say for 50 years or 60 years, but nowadays we should not lose the opportunity to record the data which can be used in future. This is the reservoir, and these are the stations which we deployed around Tiri. We are thankful to TSDC to have recognized this, and a very long-term planning for seismicity studies they are going on. The 6-station telemetered array, sample array, it was a sample array in Himalayas, and I'm fortunate enough to start my career in 1985 when we deployed it around Tiri. So this was a 6-station array which was then upgraded to 12 stations, and we are now going for 18 stations, and ultimately 23 stations will be deployed. So these type of instruments, they are deployed there. It is a telemetered array. All the information is coming in real time to New Tiri town, where we are recording this seismicity. So 9 stations are radio telemetered, and 3 stations are standalone, and we are having a central recording station at New Tiri. So when we are doing, I'll just give you a little bit background that in data processing, we are collecting the data continuously, and then we are processing it for the phase identifications. You know, there are P and S phase and the surface waves which are coming. Then using some of the software, we are locating and finding the time. And this information we are regularly giving to TSDC. Then we are refining the locations, we are estimating the source parameters, and then we are giving the depth sections and the seismicity map for annual report. And there are many PhD students and master students who are doing advanced research, which I will be showing you later in this talk. We are carrying out about 4 types of things. One is the basic thing, where the data collection is there, and we are putting this data, archiving this data for the future use. Then the simple things, where we are locating the events, finding the epicenters, associating them with the tectonic features to get the seismotectonic model of this. Then we are looking into the temporal and spatial variations, including the depth sections. Then calculating the hazard parameters, the focal mechanism, source parameters, and other analysis. For example, this is the number of earthquakes per year. So you know whether they are increasing or decreasing with time, with number of events, within 20 kilometers, 40 kilometers, with focal depths. Then whether they are clustered in some particular sections. You get the depth sections. You know how they are behaving with depth. You know how the focal mechanism is working, the sense of motion below the dam. You may know this is also for another dam, which is Italian. Then you can find how the energy is being radiated from this. What is its relation with the magnitude, the frequency, the source size. This is very important and it may be interesting to you. You can see the variation in seismicity with respect to the level of the water in Tiri Dam. So you can know whether by filling it or otherwise, whether there is a variation of seismicity or not, which will give you idea about triggered seismicity. Then you can find the three-dimensional model below the dam, which will give you the idea of how the sources are varying. Like in this case, we have found a ramp. Now in future, if I want to recalculate and re-estimate the seismic hazard, I will be concentrating here rather than the old models where I know that there is a decollement going on. So this type of advanced research is also going on. This we have done for Coal Dam, Lakwar Dam, Italian Dam, and in the past for around 15 dams or so. So, and then the strong motion is one of the important part. This has to be inside the body to find the response. So in Tiri, we have deployed it in the Tiri Dam body, the powerhouse and the Koteshwar Dam. The strong motion recorders, they are deployed there. And we have recorded many earthquakes there, which are far away from this. But how much strong motion in terms of peak ground acceleration or peak ground velocity or peak ground displacement they are giving at the site. These information will also give you some idea about health of the dam, because you will be able to find the response of the dam in wake of the strong motion, and then you can recalculate the period of the dam and find whether there is some deterioration in the material properties or not. So we have been doing this in past, and these are one of the very important studies. That's what I want to emphasize here. Thank you.
Thank you very much. One very fast question. All the others go through the writing process.
Myself, Dr. Alok Mahapatra. Basically, I am the Chief Geologist in Government of India, PSU. Sir, I have one question. So, for the seismic hazard assessment, BSI already developed this seismic zonation map in 2002. After that, also, we have done a lot of work in microzonations, like the Bangalore, Kolkata, and the metro cities. But till now, it is not developed any typically like the 2002 BSI map. Till now, it is not developed the seismic zonation map of India, in which basis any project, the costly projects would be built within that period, within that environment. First question. So that is the planning of the expertise from that, they have to concentrate on that. Second is that, sir, whatever you have considered the PGA or a seismicity or whatever may be for any analysis of the particular region, subject to the tectonic features. So can you consider for the seismotectonic analysis of any dam of India in which they have concentrated on the seismicity as well as the tectonic features, geological tectonic features, because these are the two parameters very vital for any construction.
Okay,
Please conclude.
I got the questions. The first question is why we are not updating these values. So for your kind information, BIS is always updating the maps. There is a map subcommittee which is taking and considering all these things. And for this audience, let me tell you that the seismic hazard assessment for South India for a specific point is already in pipeline. And I was thinking that it may be inaugurated in this conference, but that seismic hazard assessment, you can have the values at any point by just marking the point. It is a dynamic system which is developed, and you will get it very soon. The second question is, you have answered the query in your question itself, that whether we are taking into consideration the tectonic processes and all that. While making the seismotectonic model of the area, we are considering the seismicity, we are considering all the geophysical anomalies, the geology, the tectonics, And all these forces, after which we associate the seismicity, and that is what is called as seismotectonic model, which is considered while estimating the seismic hazard. So you are very right. We consider all these things, and you have answered this in your question itself. Thank you.
Thank you. Let's keep moving. So now we welcome Mr. Rajesh Pandey, and we'll ask him very kindly to introduce himself and make, again, good use of your 10 minutes.
Which one, sir? This one, huh? Yeah. PowerPoint, huh?
PowerPoint. Yeah.
It's not opening. Sir, another copy.
Just as.
Okay. What about this, sir?
No, it's this one only.
No, sir. Sir, okay.
Yeah, it's done.
No, it's okay.
No, it's not opening. Why it's opening? You have a इनके पास होगा ना?
It's hanging. I think graphics may be too much. That's the reason.
नहीं है क्या? एक मिनट इसमें देख लीजिए. ये वाला देखिए ना. इसमें भी है.
Just a minute.
इसमें भी देखते हैं उसको.
Percentage is already loaded in this, no?
No. That is presentation is not here.
But that you should not allow. You should insist that it should be loaded. Otherwise, let them. No. The rule is applicable to everyone.
This one came ना? This one. This one. Namaskar, I am Rajesh Pandey from Dinosaur Concrete Treatment Private Limited. We are a Mumbai-based company working in the field of underwater repairs and as well as above water repairs. You see, this project we are today discussing is one underwater repair we have carried out in Sri Salem. The structure was basically an exist structure for a hydropower plant which was working in both mode, turbine and pump mode. In the exist structure, there was a trash rack structure installed at the outlet. There was 12 numbers of vents and outlet structure having 14 number trash rack of the sizes. This is basically a typical arrangement. During one generation mode, due to any reason, it was not known at that time. Elements of 6, 7 and 8 number where the trash rock has been fallen down actually. And groove liner plate were wrapped, wrinkle cut or at different locations. Along with that, concrete support shoulders which are supporting the guide plates also has eroded and damaged heavily at many places. Basically, what was challenge there was, since if it was a surface condition, there wasn't any major challenge. But situation was there, exit structure, there was a 25-meter depth of water actually. And we have to reinstall entire system in 25-meter depth of water. And doing the same in the, there was two options. Either we have to dewater and make a coffer dam, that was just not possible. So we have to do entire work underwater. Major steps involved was first, as there are a lot of elements was already stuck in various locations. So first we have to do a lot of underwater cutting, using underwater cutting equipments and lifting the same out from the vents. And after removal of elements, we have to remove the various guide plate which was in different shape actually due to these damages. After that, we have to plot the mapping actually on the very micro level, since elements have to replace the same conditions, and that's why we have decided to carry out the underwater survey. However, the problem was that the underwater survey which we have to carry, we don't know exactly where the plates or where the concrete has been damaged and what locations. So basically we tried then, first we decided to remove the elements and all. After that we carried out the survey to assess the damages and locations of various plates. For assessing the damages, there was not any particular method where we can know what is the damages actually. So we created one innovative solution which was designing customized templates and manually lowering the same in the vent, so that we can know that where it is stucking and what is the damages are there. This was basically a template which was created using a central segment which was a fix and two left and right segments which was movable. And using this left and right segment we can move in the vent actually, and the same was lowered using a derrick. And the center line of this vent was aligned with the center line of the template. However, the size of template height we kept just a half meter, 0.6 meter actually, because there was chances of stucking it during the operation actually. This was basically template. Now the template has, as you can see, there is red color and black color, which can give us the vent dimension actually, and along with there was another problem which was the measurement of grooves also and bearing also. There was 3 dimension in any vent actually. So with this unique system we will able to measure, and after measuring the same we can plot in a graph, so we can know where the depth, width of the elements has, width of groove has been changed or the same can be mapped. After this was basically mapping where was the damages are there. After this we found that the reason was that you can see many locations during the construction stage, vent size was less, or groove width was lesser side, or bearing was not available. It was during the construction itself. So element which was fixed during the construction, the contractor who have done it, he has just by pressure or by any method he just installed it and left it like that. So after the operation, what happened when this generation started, wherever the loose elements was there, it got fallen off. You can see that the blue and red color is actual and blue color is the dimension actually as per design. So groove width was lesser size, many places higher sides. Like bearing, you can see bearing actually, red color was actual, but however design should be as per the blue color. So this was the various problems which was there. Now entire thing we have to create in underwater. So we created a unique system of installing an angle actually. So angle RN of ISA 60 by 65, so that can act as a angle, and simultaneously we welded one MS plate along with the angle which can create the gap of the flange plate. So using this type system, wherever the differences was there, we can able to provide the extra bearing as well as actual group width which was required. And after installing the same, we using underwater drilling machines, we fix the same using a anchorage system along with anchoring compounds. Third problem was this concrete which was damaged, after along with the guide plates, lot of concrete has been removed from the concrete structure. So the flange plate which we have, this is the system basically. Flange plate which we have installed, after installing the same with the groove plates, bearing plates actually, the same has been filled using underwater setting epoxy fill-rise grouts actually. So that whatever the concrete damages was there, that can be reinstated with the help of epoxy concrete. This is the basic dimension of the same. at different location where we could not, since as I already informed, the entire depth was up to 25 meter. So at many locations, drilling itself was taking hell lot of time, because during at higher depth, actually drilling itself was not feasible, or it was taking so much time. So we have to create a unique system where we just drill entire system at the, fix entire system at the top using the customized templates, and fix at the, by using bolts and nuts in the underwater. For repair scheme, wherever only damages was there, we fix MS plates using GI sheets and fill the same with epoxy grout. This is basically a design of epoxy grout wherever the only concrete was there. Formwork, which was for groove liner, the same was used using the nut and bolts. Entire operation everywhere you can say is the country carrying out was underwater. This was also a specialized formwork. Challenges and solutions which was found at that level was, entire work was to carry underwater various depth or level. As you might be knowing that in the working the depth, there are a lot of challenges, because the divers, there are limitation of working. Any diver have to go as per the depth wise. So suppose 25-meter depth is there, so he cannot work more than 20 minutes actually, a particular diver. So we have to provide a lot of numbers of divers along with equipments, breathing equipment, saturation diving equipments and all. And along with that, health checking of the divers was very important. Difference which we found was actual and actual and design dimension. That was a challenge which we have to create using unique systems. As for the material which was concerned, that material which was chosen, that should be cured in underwater. It should flow, because entire material was flown from the top. So that should flow in the water, and it should gain strength in the underwater and does not dissolve. And it should also achieve high early strength with moderate setting time, because that was another challenge, because in generation you can know that operation of plant is also very important, which cannot be kept for a long time. So that was another challenge. That's why we have to do entire work in only 25 days of shutdown. So that was a very big challenge for us. After this installation of entire thing, we have again reinstalled the templates and moved in the groups, and then found the entire templates were moving very good. So that was, entire operation was carried out very successfully. I have one small video of the same actually video clip. I will show you that. Can you help somebody? I have time? Video? Yeah, a small video. Have you seen?
Which one, sir?
Sri sir.
This one? Sorry, sir.
This was basically underwater cutting, which is happening to remove the elements which are stuck in the groups, as I told. And this is the basic checking the width actually, mapping for the damages actually. You can see the bars which were provided to measure the width of a groove and along with the bearings. Hardly 2 minutes. I'll move.
No, because if the voice was So we are not taking any fast question this time to advance a little bit of time. So I'm going to ask next speaker to get ready, Mr. Ravindra Pade. Please come to the podium, prepare to introduce yourself, and let's thank our previous speaker.
Thank you very much.
So, Ravindra Bhatta.
Protection Ravindra Bhatta.
Can I open?
Just these things.
Yeah.
Okay.
You can use this here also and use this also. You can use here also the button and this also.
Okay. Good afternoon, Chair and delegates. I am Ravindra Bhatte, Scientist B from Central Water and Power Research Station, Pune. Cavitation on spillways. Spillways are the significant and most integral part of spillways are the most significant and integral part of any dam body, which is used to convey the flood water from the reservoir to the downstream safely. When we are considering the spillways with high head or high head spillways, the flow velocity over the spillway will be very high and maybe of the order of 30 to 50 meter per second. And when such a high velocity flow is over the spillway, then there are chances of cavitation due to the flow separation or surface irregularities on the spillways. Cavitation is a complex hydrodynamic phenomena where at any point in the water mass, the water pressure goes below the vapor pressure and the vapor cavities are formed. And these cavities flow with the water mass to the downstream where the high pressure, in the high pressure zone they comes and they implodes. And with the implosion, a shock wave or a microjet is formed, and if it is near to the spillway surface, it will damage the spillway surface. This action is called as pitting, and continuous action, pitting action will damage the spillway surface. The factors which affects the cavitation are flow velocity, duration of flow, surface material, entrant air, and surface roughness and alignment. But the most important factor is the cavitation index. The inception of cavitation damage on spillway can be assessed by the cavitation index, and the parameter sigma is seems to be the more realistic and the rational one. Here you can see in the formula V is in the denominator. So for the high velocity, the sigma will be lower, and as the sigma will be lower, the chances of cavitation over the spillway will be higher. These are certain photographs which depicts the cavitation on the mammoth structure like spillway and what cavitation can do with the spillways. And if the spillway is in danger, there will be certainly the dam will be in danger. There are methods of prevention of cavitation damage. There are prevention of cavitation from occurring, use of damage resistant materials, and forced aerations. The prevention of deviation can be done by proper design of spillway, strict surface tolerance, or limiting the cavitating velocity. You can operate the spillways with lower head so that the cavitating velocity will be less. The damage resistant material like high performance concrete, steel fiber reinforced concrete, epoxy or polymerized reinforced concrete can be used, or the material like stainless steel can also be used for cavitation resistance. And for forced aeration, the use of spillway aerators are the most economical and popular way of the mitigating the cavitation. The aerators are the devices or the arrangement which is provided on the spillway surface in such a way that the flow is lifted from the bottom and a sub-atmospheric or void is created, and that demands the air, and the air is demanded, air is supplied through the air duct. It is shown from the literature, or it is can be seen from the literature, if the air content in the flow is 6 to 8%, the chances of cavitation can be eliminated. The aerators have been used worldwide for mitigating the cavitation. on the major dams like Tarabella, Glen Canyon, Hoover or Karun. They are used as the corrective measure, and they have included in the dams like Sardar Sarovar, Indira Sagar or Tehri Dam. I am here discussing the case hydraulic model studies which are conducted at CEDU Paris for orifice spillways which are having more than 50-meter head over the spillway crest, and for which the cavitating pressures were there, and for different case the solution was different. Here you can see the 1:40 scale 2D sectional model which was constructed at CEDU Paris, and the studies were conducted on the spillway of size 6.1 meter by 12.6 meter, which has to cater the design flood of 12,981. The discharge intensity you can see here, it is of the order of 300 meter cube per second per meter. The pressure profiles over the spillway were measured for different reservoir water levels and for different discharges for gated and ungated conditions. In this case, for gated conditions, the pressures over the spillway were found to be positive, but for ungated conditions, the cavitation susceptibility zone was found. From the figure, you can see the cavitation susceptibility zone is of the order of from chain is 22 to 63 meter for 25% discharge, and it was from 34 to 56 meter for 100% discharge. There were possible remedial measures to mitigate these cavitations where the provision of aerator, surface protection or the elimination of cavitating velocity. This is the view of the river. This spillway was typically on Himalayan boulder river which carries heavy sediment and the boulder size of 0.2 to 2 meter, and these boulders will roll over the spillway during the flushing operation or during the floods, and this will certainly damage the aerator. So the option of aerator was ruled out. So another thing was thought that the limiting velocity over the spillway can be reduced by reducing the head. So the spillway crest was raised by 5 meter, and if you compare the cavitation index for the original and modified design, you can see the cavitation index was greater than 0.2 for all the cases of discharges, 25 to 100%. So the cavitation was mitigated. This is another case where the pressure over the top surface of orifice spillway was of the order of minus 0.13.5 meter. So hydraulic model studies were conducted at CEDU Paris and 1:40 scale 2D sectional model, and different alternatives were tested. It was found from the alternative 3, which with the 45-degree tangent to the vertical face was found to be suitable, and the pressure were reduced to minus 3 meters. This is another case of two-tier spillway, where for the sluice spillway or the bottom spillway, you can see the head over the crest is of the order of 65 meter. 5 different spillway design alternatives were tested for the hydraulic conditions or getting the proper acceptable pressure conditions, acceptable pressure over the spillway, but it was found that pressure for all the design alternatives were negative and cavitation index were found to be less than 0.2. And in this case, you can see the tail water level is very high. So the provision of aerator was not possible here. So it was suggested, or it was discussed with the design engineers and suggested to provide the steel liners for protection of cavitation of the sluice spillway. This is another case which is the spillway of size 11.5 meter by 14.7 meter, which has to cater the flood of 35,000 meter cube per second with very high discharge intensity, and the model was constructed at CEDU Paris, and the piezometric pressures were measured, and from the pressures it was found that the pressures were positive for the ungated operation of spillway, but for the gated conditions the negative pressures of the order of -1 to -6 meter were found with the cavitation index well below 0.2. Here also 3 different crest profiles were tested on the model, but for every crest profile the pressure over the spillway surface were negative and cavitation index was below 0.2. So here it was decided with in consultation with design engineers that the aerator should be provided, and the aerator in the form of 0.25 meter ramp and 2.5 meter step was provided, and it was tested on 1:25 scale aerator model. From the bottom graphs you can see after provision of aerators, the pressure over the spillway surface were improved significantly, and the pressures were tested for gate opening of 10% to 70% and at different water levels. So coming to conclusions, we can say that mitigating cavitation damage over high head spillways has been a challenge for the designers. Aeration is supposed to be the best method for eliminating cavitation of spillways, but the hydraulic and operational constraints compel the design engineer to opt for alternative options, and hydraulic model studies plays important role to predict cavitation chances on the spillway. Thank you.
So, having reached this point, and as there's plenty of action in the exhibition hall and the other room, I think we are going to collect. Please make sure to submit your questions. The organization will make the questions arrive to the speakers later on. And let me ask for a kind applause for all the speakers. Also for the reporter and the court chair. and co-chair, and the chair, and hope to see you outside. Apologies for this noise. We tried to keep on time. We did our best. So let's keep going with the conference. Thank you for attending. And the organizers. Thank you to the organizers, of course. Just a second.
Okay, with the permission of the chair, I would like to take this opportunity to announce the last part of the session, that is distribution of mementos. As a token of love and respect to the eminent speakers of this particular technical session, we would like to distribute mementos to them. For that, I invite the respected chairman for distributing this mementos, and for receiving the memento, first of all, I call Dr. Hadush S. Hagos to the stage. Okay, sir. Now I invite Dr. M.L. Sharma to the stage for receipt of this memento. Now I invite Mr. Rajesh Pandey to the stage for receipt of this memento. Mr. Rajesh Pandey. Now I invite Mr. Ravindra Arbate for receiving the memento. Now I invite Professor Santosh Thambi sir to receive the memento from our respected chairman. Now I invite Dr. Mukesh Kumar Sinha, co-chairman of this session, for the receipt of the memento from respected chairman. Now I invite Sri M. Gopalakrishnan former Secretary General ICID and former member Central Water Commission, New Delhi, India, to the stage for presenting memento to the respected chairman of this session. Thank you.
So now we are closing the session. So please go to the exhibition hall and take advantage of this wonderful conference. Thank you again for coming.
ഹലോ മൊബൈൽ കണക്ട് കൊടുത്തു നോക്കാൻ ചേട്ടാ ചേട്ടാ മൊബൈൽ കണക്ട് ചെയ്ത് വയ്ക്കണം മൊബൈൽ കണക്ട് ചെയ്ത് വയ്ക്കണം മൊബൈൽ
Measurement on the bottom of the bar.